Okay, I want to talk about number 1969 on the BC test, number 10. And this is really a trick question, and I wouldn't have figured it out until I looked at it years ago. It's a little trick that they use to set this problem up. Again, I wouldn't give you this kind of question or expect that you'd be able to do this on a serious test, but here it was on an AP test. So what we do is we're going to add 1 and subtract 1 from the numerator. So a net change of 0 in the numerator. And then what we're able to do with that is we're able to split up the numerator. You can always split up the numerator as long as you leave the denominator the same. So I'm going to split it up in this way so that you have x squared plus 1 over x squared plus 1 and then minus 1 over x squared plus 1. Obviously the x squared plus 1 over x squared plus 1 becomes 1. Okay. And I forgot all the dx's there, so you do need to have them in there. So we get the integral from 0 to 1 of 1 plus 1 over x squared plus 1. And 1 over x squared plus 1 is tangent, if you recall. That is the derivative of the inverse tangent function. So the integral of 1 over x squared plus 1 is going to give me the inverse tangent. And the integral of 1, of course, is x. And so we have x plus tangent inverse of x. We're going to evaluate that at 1 minus the same expression evaluated at 0. So for 1, so for the first one, it is x is equal to 1. What is the angle whose tangent is 1? And that would be pi over 2. Sorry, that should be pi over 4. Then for the second expression, x is 0, and the angle whose tangent is 0 is just 0, so the whole second expression evaluates to 0. And that leaves us with 1 plus pi over 4, which can be simplified to 4 plus pi over 4, and so the answer is E. Great question, and I would be surprised if anybody were able to solve it that way without asking the question. So that's how that one works. All right, in number 23, this is what we call a differential equation. We have dy dx is equal to something. And the way we're going to solve this is using the separation of variables technique that we talked about, albeit briefly, in class on Thursday, I guess it was. So I'll set this up and you'll see how this goes, how this works. Alright, so I'll move the problem over here so I have a little more room. Now what we need to do with this is separate the y's onto the same side that the derivative is on. And the way we'll do that is to multiply both sides by y. And then what we're going to do is take the integral of both sides with respect to x. And when we do that, we do get some cancellation. And we end up with integral y dy. And so we have these two integrals. On the right side, it's negative integral x over e to the x squared dx. All right? On the right side, it's going to be y to the second over 2, left side rather. And on the right side, we're going to need to do a u substitution. We're going to let u be x squared. And it might even be easier at this point to let u be negative x squared. And so I'll show you how that is written. So we'll go back to writing the integral as integral negative x e to the negative x squared dx. For our u substitution, we'll let u equal negative x squared. So that du is negative 2x dx. And 1/2 du is equal to negative x dx. So and then negative x squared is just u. Excuse me. So we have integral e to the u du. Or actually 1/2 integral e to the u du. Now because this is a definite integral, I'm going to swap out my limits of integration. Sorry, it's not. I'm giving up an initial value, and that's the way I'll solve it complete in the next video.